system can be classified based on the stability of the system. We have three different cases. Absolutely stable means for any input the system is stable. Stable means the output graph there is no fluctuations. Output graph there is no fluctuations. Okay, it is going to a finite value. So stable means output is going to a finite value. Okay, at t approaches infinite. At t approaches infinite. That is stability. And this occurs for all input, any type of input. Okay, for all input, this occurs. That is called absolutely stable system. So conditionally stable means this happens only for a range of input values. So output is finite value. Okay, all this happens only for range of inputs. Range of inputs. If this condition holds good, then it is called conditionally stable. Marginally stable means it is a neutral condition. It is a neutral condition. It can be unstable or it can be oscillations. It can have oscillations. The main thing is it can have oscillations. This will happen when the poles are located on y-axis. Poles on imaginary axis are there, then we call it there is oscillations and the system is marginally stable system. Okay, so y-axis or imaginary axis or j omega axis, one and the same. Okay, y-axis or imaginary axis or j omega axis in the pole zero plot. In pole zero plot. Okay, so if poles are located on y-axis, then we will have the oscillatory nature for the output graph. In that case, the system is called marginally stable. Okay, we have seen what is absolutely stable. Conditionally means only for a range of input values or component values, system is stable. And marginally stable means the poles are located on y-axis. So this marginally or critically stable, sometimes it may become unstable when repeated poles are at the same location. On y-axis, we are having poles. When repeated poles are there on y-axis at the same location, then it becomes unstable. Okay, that's why the reason critically stable means at any time it may become unstable. That is the case. Critically stable means at any time it may become unstable. When such thing happens, when repeated poles are there on y-axis on the same location. Okay, so for example, if I draw the pole 0 diagram, this is x-axis, y-axis. I am having plus 2j and minus 2j. Two poles are there. Okay, this is called marginally stable system. This is called marginally stable system. But if I have repeated poles at the same location, which means plus 2j plus 2j. Okay, 2 times I have plus 2j plus 2j and 2 times I have minus 2j minus 2j. If this is the case, okay, if this is the case, then it is unstable system. Repeated unstable system. Okay, so repeated poles on y-axis at the same location, Okay, so that is unstable system. So all these are the different things in stability. Now I am going to Routh-Hurwitz stability criteria. Routh-Hurwitz stability criteria. Otherwise, it is also it can also be called as RH criteria. It can also be called as RH criteria. RH, Routh-Hurwitz is the scientist name. So it can also be called as RH criteria. Now, if you see the main important points, we will be generating a data table. Okay, in RH criteria, it is called, the table is called Routh table. Okay, we will be generating a data table, and this is generated using characteristic equation. So what is characteristic equation? Definitely you will have a question in second internals. So it may be one word answer or any model. What is the definition of characteristic equation? It is the denominator of closed loop transfer function. It is the denominator of closed loop transfer function. So using that characteristic equation, we will prepare a table. That is the method in RH criteria. Okay. So how to prepare? We will take up a problem and see. And after preparing the table, what we have to check? Whether the first column, all the elements are having no sign changes. First column doesn't have any sign changes. We have one necessary condition and one sufficient condition. You can see one necessary condition, okay, and one sufficient condition in RH criteria. RH stability, one necessary condition, one sufficient condition. So generally, if you see, this is the characteristic equation general format. I am taking this equation 1. This is the general format of characteristic equation. Okay, you can see A naught S power n a1 s power n minus 1, a2 s power n minus 2, like that an equation is present. Necessary condition is all the coefficients should be positive. Okay, here the coefficients are a0, a1, a2 and so on. All these are called coefficients in the characteristic equation. All these are called coefficients in the characteristic equation. Okay, so if all the coefficients are positive, that is the necessary condition for a system to be stable. Sufficient condition means after making the first column, after making the RH table, okay, data table from the characteristic equation, the elements of first column should have no sign change. Okay, they should have same sign, otherwise no sign change. These are the important points in RH criteria. These are the important points in RH criteria. And how to calculate each and every value when we take a problem, I will detailedly explain. Okay, I will follow this procedure to do the RH table. So this is about the details. This is the problem. We will take up the problem and solve. This is a general thing. This is called RH table. What we are doing is RH table. And this is equation 1, characteristic equation. Okay, the RH table is below. We will take up a problem and see how to do it detail. So whatever we discuss in RH table, I will just note down the points. The closed loop transfer function, we know closed loop transfer function, okay, which is G by 1 plus GH, and the system is present G, H, and input side it is R of S, output side it is C of S. We are trying to get the closed loop transfer function, and in the closed loop transfer function, denominator, okay, of closed loop transfer function is characteristic equation, and the general format of characteristic equation is a0 s power n, okay, a1 s power n minus 1, a2 s power n minus 2, like that, okay, and a n minus 1, okay, a n minus 1 into s plus a n s power 0, So you are having s power n to s power 0. You can see this equation. We are starting with a0 s power n, okay, and we are having n plus 1 terms, because s power is 0 to n, a coefficient suffix also 0 to n, okay, n plus 1 terms are present. This is the general representation of characteristic equation. So we have to prepare RH table. Okay, from characteristic equation. And in the RH criteria, we have two things: necessary and sufficient condition. Okay, we have necessary condition, sufficient condition. Necessary condition and sufficient condition. I will come to this once I finish the RH table. From the characteristic equation, how to draw the RH table. For example, if you have 3s cube, 4s square, and 5s plus 2 equal to 0. Okay, let this be equation 2. Let this be example of characteristic equation. Now RH table, we have to start with the highest power of s. S power 3, s power 2, s power 1, s power 0. Okay, so whatever s powers are there, we have to write it. This is the table I am going to prepare. And now what we have to do, take the alternate terms, s power 3 term and s power 1 term. You write the coefficients in the first row. And then take the even powers of s. S power 4, s power 2 coefficient, s power 0 coefficient, you write in the second row. Okay, so odd terms, first term, third term, fifth term, like that I am writing in the first row. Even terms, second term, fourth term, sixth term, like that I am writing in the second row. Okay, now I have to go with the calculation. 2 rows completed. Row 1, what I have done, row 1, it is odd terms, okay, in characteristic equation. Row 2, what I have done, even terms, second term, fourth term, etc. from the given characteristic equation. Now, 2 rows completed. S power 1 row. I have to find the values for S power 1 row. Okay. So, what I have to do, I have to multiply like this. 4 into 5 minus 3 into 2 divided by 4. Okay. So, 4 into 5 minus 3 into 2 divided by 4. What is the value? So, 20 minus 6, 14 divided by 4, which is 7 by 2 or 3.5. I am writing 3.5. Okay. Now, going to the next element calculation. Next element, here I have to calculate value, okay, for which I have to proceed like this. So for the next term calculation, I have to proceed like this. Here no elements are present. Okay, I have to calculate, for if no element, it is 0. 4 into 0 minus 3 into 0 divided by 4. Okay, so 4 into 0 minus 3 into 0 divided by 4, which is nothing but 0. So here elements will not come because the next further elements are not there. We are not able to calculate the values in the S power 1 row. Further values are not able to be calculated in S power 1 row. So only one element is present. Now I am going to S power 0. S power 0 row. Now I am going to S power 0 row. I have to proceed with the previous 2 rows. I have to use previous 2 rows to calculate the value over here. Okay. So now 3.5 into 2 minus 0 into 4 divided by 3.5. Okay. So 3.5 into 2 minus 0 into 4 divided by 3.5. Okay. So what we are having, 3.5 into 2 divided by 3.5, and finally the value is 2. I am writing value 2. Further elements cannot be calculated because we don't have the next elements in the previous 2 rows. Next elements are not available in the previous 2 rows, so further elements cannot be calculated. Okay. By this RH table completed. By this RH table completed. Now what we have to check, number of sign changes in the first column. Number of sign changes in the first column. Okay. So if there is no sign changes, then the system is stable. Then the system is stable. That is the sufficient condition. Okay, that is the sufficient condition. Now I am going to necessary and sufficient condition. So necessary condition is nothing but, okay, necessary condition is nothing but all coefficients in the given characteristic equation should be positive. All coefficients in characteristic equation should be positive. Okay, so equation 2 is our characteristic equation. You can see all the coefficients 3, 4, 5, 2, all the coefficients are positive. That is the necessary condition, but that is not enough to decide whether it is stable or unstable system. Okay, so that is the first condition we have to check from the given characteristic equation, whether all the coefficients are positive or not. If all are positive, that is necessary condition, halfway satisfied. But we have to complete RH table and check whether any sign changes. This is positive 3, then positive 4, no sign change. Okay, positive 3.5, positive 2, there is no sign change. Sometimes if it is minus 3.5, you will be having positive to negative, one sign change, again negative to positive, another sign change. In that case, 2 sign changes are there. Okay, if the last element is negative, last element 2 is negative, then only in the last case we are having sign change from positive to negative. So number of sign changes equal to number of roots on the RHS. Okay, in the pole 0 diagram, number of poles on the RHS is nothing but number of sign changes in the RH table. That is sufficient condition. Sufficient condition means we have to check the first column in the RH table. First column in the RH table. Okay, first column in RH table. So these are the 2 conditions based on which the stability using RH criteria can be concluded. Okay, stability based on RH criteria can be concluded using these 2 points, necessary condition and sufficient condition.